Let us next start the exercises. And in these exercises, there is a comment in the beginning itself, unless otherwise specified, symmetric and skew symmetric refer to transpose. That means they don't refer to general adjoint. So let's see what this second one is. We have to use a trace argument to prove that if the characteristic of the underlying field F is 0, then it is impossible to find two matrices A and B in the matrix algebra Fn such that AB minus BA is the n by n identity matrix. Okay, so this is the solution to part A. Contrary to the claim, we have supposed that such matrices can be found, A and B in Fn, for which AB minus BA will be equal to the n by n identity matrix. Then what we do, we take trace on both sides of this equation, and that gives us this. Trace of the n by n identity matrix is n, sum of the leading diagonal entries, which are all 1, and that equals trace of AB minus BA. Now using properties of trace, this becomes trace of AB minus trace of BA. However, another property of trace says that these two traces are the same. That means we should get 0. However, we are in a field of characteristic 0. So no positive integer should be equal to 0, or more accurately, more precisely, no positive integer times the unit element of the field 1, which is what n actually means, should be equal to 0. And that happens because F has characteristic 0, which means that this supposition is false, and that proves the claim. Next we have part B. In part A, we proved that AB minus BA cannot be equal to 1. In other words, 1 minus of AB minus BA cannot be the 0 matrix. Here, more generally, we have to prove that not just the 0 matrix, but it actually cannot even be nilpotent. Again, here also the solution is similar. We suppose that no, this is in fact nilpotent. Then its trace will be 0, because nilpotent matrix only has the 0 characteristic root, and we have already seen that the trace of a matrix is the sum of its characteristic roots. So 0 becomes equal to the trace of the matrix, but then again you apply the properties of trace, that gives you trace of the identity matrix minus trace of AB minus BA, which itself is trace of AB minus trace of BA, and this part vanishes like part A. So we again get n, but then again n cannot be equal to 0 in a field of characteristic 0. So this is not possible, and that is why our supposition is wrong. So the matrix cannot be nilpotent. So it proves the claim. Next we have 4a. Here the underlying field has an infinite number of elements. Then we have to prove that every matrix from the matrix algebra Fn can be written as a sum of regular matrices. That means invertible matrices. Okay, so this is the solution. Say A is any matrix in Fn whose ith row jth column entry is alpha ij. Now the fact that F is infinite, I mean our field is infinite, allows us to choose a field element alpha which is non-zero, and at the same time it is different from all the minus alpha i's. The additive inverses of all the diagonal elements of A are different from alpha. No matter how large this n is, that is, no matter how many alpha i's we have, the infinite nature of F allows us to choose alpha such that it's different from the additive inverses of all of them, and at the same time it is not equal to 0. Alright. So now how can we write A as a sum of invertible matrices? This is one of the ways. So here what we see is that this is a lower diagonal matrix whose upper diagonal, of course, that off diagonal entries are all 0, which is indicated by this 0. The diagonal entries are all 1. What is this lower diagonal part? This lower diagonal part is actually the lower diagonal part of A. Fine. So those things have already appeared here. What else do we have? In this second matrix, the diagonal entries are all -1. Here the lower diagonal part is 0, but the upper diagonal part has what A has in its upper diagonal. So if you add these two matrices, the diagonal then becomes 0 because 1 and -1, and the off diagonal entries taken together, I mean upper off diagonal as well as lower off diagonal, give us all the off diagonal entries of A. So that means in this part itself all the off diagonal entries have already appeared. But then what about the diagonal entries? They are then next taken care of by these two diagonal matrices. Here 0 here and 0 here, these zeros indicate that these matrices are diagonal. And if you look at the diagonal entries and add them up, corresponding diagonal entries, then you get the diagonal entries of A. So that is why this entire sum is equal to A. Why are these matrices all invertible? We know that a triangular matrix, this is a lower triangular matrix, this is an upper triangular matrix, is invertible. It's a problem that we have already seen and solved, provided all its diagonal entries are different from 0, which is the case with these two triangular matrices. So they are invertible, and these diagonal matrices are invertible because the diagonal entries are different from 0. Here minus alpha is different from 0, and here all these diagonal entries are different from 0. See? That is why we have been able to express A in this way as a sum of regular matrices. And the fact that F is infinite has helped us to do that. So that is part A. Part B, again our underlying field F is infinite, and we now have a function small f from the matrix algebra Fn to itself, and it satisfies these three properties. F respects matrix addition, F respects multiplication of a matrix by a field element, and F also satisfies this third property that f of B inverse is equal to f of A, and all these properties of course are true for every A in Fn and every B in Fn for the first property. For the second property, for every A in Fn and every field element lambda, and for the third one, for every A and B in Fn where B is invertible. If so, then we have to prove that f of A is alpha naught times trace of A. So there exists a scalar alpha naught. I did not get space here to write more than this, which is fixed, okay, which does not change, and for that alpha naught, f of A is actually alpha naught times trace of A for all A belonging to the matrix algebra. This is what we have to prove. Solution. We take two distinct indices I and j. Then Eij, the matrix Eij plus the n by n identity matrix is invertible. You remember what Eij is. Eij is that matrix whose ith row jth column entry is 1 and all the other entries are 0. If you add the n by n identity matrix to that, that becomes an invertible matrix. Why exactly I won't tell you. You should be able to get this fact from properties of triangular matrices. I will tell you only this much. And in fact, its inverse is minus Eij plus 1. Now next what we do, we form the conjugate of the matrix Eii by that matrix Eij plus 1. So Eij plus 1 times Eii times the inverse of Eij plus 1. So if you perform the multiplication of this one and this one, then you have Eij Eii, which becomes 0 because j is different from I. You also recall the rule for multiplying two such e's. If you multiply Eij and Ekl, say, then the product will be 0 if those intermediate indices do not agree, if they are not equal. Otherwise, Eij times Ekl will be equal to Eil if j and k are equal. Here the intermediate indices j and I are not equal, so this product becomes 0. 0 plus 1 times Eii is Eii, and the inverse of this is this. So then again applying that rule, if you do this multiplication, here the intermediate indices are same I. So the product is minus Eij plus Eii. Alright. Now by applying the third property of the function f, the f value of Eii will be equal to the f value of any matrix similar to Eii, and this is one such matrix because it's the conjugate of Eii by that invertible matrix. So f of this should be equal to f of this. However, this is equal to this thing minus Eij plus Eii, and then again using the first two properties of f, that equals minus of f of Eij plus f of Eii. So you can see that f of Eii and f of Eii can be cancelled from both sides, which gives you the fact that f of Eij is equal to 0. Okay. So if I and j are distinct indices, then no matter what they are, f of Eij is equal to 0. There is one more fact, and this fact is about the Eii's. Any two such matrices are similar to each other, they are permutation similar. That is because Eii, for example, is the diagonal matrix whose ith diagonal element is 1, all the other diagonal elements are 0. Similarly, Ejj is the corresponding such matrix whose jth row, jth column entry is 1 and all the others are 0. And by row and column interchanges, you can turn Eii into Ejj. So they are permutation similar, and because they are similar, so their f values will be the same, and that is why f of all these Eii's are equal no matter what I is. Now let's see what we get from these things. Let us take that itself as our alpha naught, and then let's see what we get if we calculate f of a with all these things set up for us. You know that you can express A as a linear combination of the matrices Eij, where I and j both vary from 1 to n independent of each other. So that's why there are two indices in this sum. You can view it as a double sum also. And in fact, the coefficients are nothing but the entries of A, the alpha ij's. So you then have this sum, because f has those first two properties, that it respects addition as well as multiplication by a filled element. So f goes inside the sum and gets applied to each Eij. And now you use the fact that for distinct indices I and j, f of Eij is 0. That reduces the sum to this. We only have those terms for which I is equal to j. That means now we can consider only one index I, which of course varies from 1 to n. We now have alpha ii plus f of Eii. But no matter what I is, f of Eii is, all of them are alpha naught. So alpha naught comes outside by the left distributive law in the field. I mean, you know, by field axioms. And we are left with this, which is nothing but the trace of A. So that's how we get this result. And that's just it for today. Tomorrow we have, I think we have analysis and differential equations. So see you tomorrow with those things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.